Here we go. Okay, so yesterday, I guess kind of like the day before that on Friday, all right, and then for the next couple days, we're going to continue working on these free response questions, okay, all the way up until our quiz essentially Friday. Okay, that's going to be kind of our goal, is just working more and more on these free response questions that keep showing up over and over and over again, kind of incorporating both like things from like way back, all right, like average rate of change and things, but also incorporating our net change ideas and functions defined as integrals, all that fun stuff. Okay, so we had left off yesterday talking about this water tank at Camp Newton. All right, it's from the Form B of an AP test. Again, so it's a little bit funkier than a typical AP test, but it's still good questions and things. All right, and so we'll kind of continue on from there. So are we all okay with A and B, and then we're ready to move on to letter C here? Is the idea, yes? Okay, so at what time t for 0 less than or equal to t less than or equal to 18 is the amount of water in the tank at an absolute minimum? Show the work that leads to your conclusion. All right, so to determine absolute minimums, all right, we need to identify our candidates, right? So what are the candidates for absolute extrema? We need to consider the what? Endpoints of the interval, so in this case that would be 0 and 18, right? And we also need to consider what? Critical values, critical numbers, right? So we find critical numbers by taking the derivative of the function whose absolute minimum or maximum we're trying to find and setting that derivative equal to 0 or to be undefined, okay? What represents the derivative of our function here? Or the rate of change of the quantity of water in the tank, right? Our function here, the thing that we're trying to, like the quantity, is the amount of water in the tank. So what thing is going to represent the rate of change or the derivative of the amount of water in the tank?
Water being quartered.
Water in minus water out, right? So the amount we'll say, okay, amount prime, right? The derivative of the rate of change of the amount of water in the tank at t is W of t, amount in, or rate in, minus rate out. Okay, water in minus water being removed. Okay, and so we want to know, when does that equal 0? All right. So again, hopefully you still have those in your calculator from yesterday. I do not, so I'll have to fix that here real quick. 95 square root of x sine of x over 6 squared. And then 275 sine of x over 3 squared. And then y1 minus y2. Okay, so there they are typed in. To do sine squared, obviously our calculator does not let us put a square between the sine and what's inside the sine, so you have to put the square at the end, right there. Okay? And so when I put the square where I have it right there, that is not squaring the x over 6. That's not squaring the x over 6. It's squaring the sine. Okay? If you want to be sure that you're squaring the sine, you can always throw another set of parentheses around the sine to kind of group it together. But it should be okay to just have the square there at the end as long as you close off the sine's parentheses. But I'll do it there anyway. Okay, and of course y1 minus y2. Now I don't want to graph all three of these things. I just want to graph the y1 minus y2. And so I will eliminate, I'll toggle off those y1 and y2s there. Okay, and then for my window, I'm going to graph from 0 to 18 because that is our interval that we're considering here. And so we'll just wait for it to finish graphing here. Okay, so there's one critical number, right? There's where our derivative is 0, and there's another critical number where our derivative is 0. So second trace, and then 0 command. All right, let's see here. I got to find where my... Okay, so there's that. Oh, I may have gone. Yep, I got to redo it. 0 command. Okay, left, right, guess. Okay, 6.495 we'll say. Okay, 6.495. So t equals 0, t equals 6.495, t equals, and then we'll do the other 0. and you get 12.975. So. And then T, of course, is 18 is your other one. Okay? So, alternatively here, instead of subtracting these and seeing when they equal 0, you could also see when W of T is equal to R of T. Right? Because if you add R of T to this side, you want to see when they're the same thing. So you can also just see where they intersect. Where does Y1 intersect with Y2 there? That's another option. Okay. And so now we need to figure out which of these gives us the greater value. Okay, which of these is going to give us the greater value? So we got to plug these back into like our original function. So let's think about what that would be. So it would be A of T, the amount of water in the tank. Okay, it started with 1,200 gallons in it. And we're going to add to that, and that was at time T equals 0. And we're going to add to that the net change from 0 to, maybe I should call this X here. Maybe I'll call this X instead. I have X. So from 0 to X of W of T minus R of T dt. So this is like a function that will describe the amount of water in the tank at any time X, I guess we'll say. Okay? If you want to know, so we start with the 1,200 and we add to it the net change from 0 to that particular X value of the water in rate minus the water out rate, dt. And so then we want to evaluate this for all 4 of these here to determine which one is going to be the absolute minimum. Okay? So to do that, you can do, in your calculator, right, 1,200 plus math 9. We'll integrate from 0 to the first one. Well, the first one's from 0 to 0, so we know our answer is just going to be 1,200 for that, right? That's easy enough. So the next one's going to be 6.495. Okay, and then we'll do, let's see here. We want to do, y1 minus y2, I believe. So vars, y vars function, y1. Or actually, I could just do y3, I guess, because it's in y3. Maybe I'll just do that. Vars, y vars function, y3 dx. Okay, so we integrate that. $525.242. Okay, is our answer there? Gallons. That's A of 6.495. And A of 12.975. Same thing. Okay, of y3. So all we have to do is change that upper limit of integration. Nice. Work. All right, 1,697.441. Okay, and then finally 18, which I think we know already. No, that's the net change, but then, oh yeah. So we know that already from, bless you, from the previous problem there, so we can just use that too. So A of 18 is 1,310 gallons. Okay. So, absolute minimum occurs where? At what time does the absolute minimum occur? 6.495. Okay, so there's the absolute minimum. So we'll just circle that. Okay. And then letter D, last but not least here. Okay. For T greater than 18. So now we're talking about beyond this interval of 18 hours. Beyond it now. No more water is being pumped into the tank. So that means which of our functions here are we no longer going to use? We're no longer going to use WT. No more water is being pumped into the tank. Okay? But water continues to be removed at the rate R of T until the tank becomes empty. Let K be the time at which the tank becomes empty. Write, but do not solve, an equation involving an integral expression that can be used to find the value of K. Okay? So, we want to know at what time, okay, does the tank kind of become empty, right? So for T values greater than 18. Okay? So, how much water is in the tank at time at 18, I guess we'll say at 18 hours? Yeah, that 1010 or 1309.788. I think you probably should be able to use either one. I'll use the more precise one here. So we'll say 1300, 1309.788. Okay, so that's at time t equals 18. Okay. And they're going to add to that. Yes, it's add because the removing part, it'll get rid of it there. The integral, okay, because we want to find the net change for the removal amount of the water. Okay. So, or actually, no, I think we do want to subtract there. My bad. We do want to subtract because the water is being taken out, and that's just going to be a positive quantity of things. Yeah, we do want to subtract there. We're going to subtract the water that's being removed. Okay. Integral from 18 to k, that unknown amount there. And then of r of t, you don't need to write the actual function. You can just use r of t dt. And we want to know when that is going to equal what? 0. We want it to be 0 again. Okay. So, yes. Okay. So there's that right there. Your amount at time 18 minus the water that's being removed from 18 to k, this unknown time, with the removal rate right there, and it equals 0. Okay? You want to know when it equals 0, when there's none left.
I got different than that, but I checked it in
Okay.
the,
Let's see here. Okay, how did you set it up differently?
I guess actually technically, I had it just your integral equals 1,300.
Right. Yep. Yeah. So that's what I actually have done here too. But yeah. So we could here you could see, because essentially we want to know when is this quantity going to be this. So this would be sufficient, but you could also say yeah. And again, they use the rounded amount there. Okay. So you could also use this one as well, or that one. Okay. Because this integral right here, we could add the integral over, and so it would be the integral from 18 to k of r of t dt. When does that equal the 1,309.788 or the 1,310 there? Whatever you prefer. But okay. So yes. All right. Questions on any of that? Okay, that was a good one. So let's turn the page here and get into the 2 that we're going to do today. All right. So we've got another curve with some area there that we're going to do. And then we have another curve with some area, but also some rate stuff as well. So important there to note that. Okay, so let's go to number 22 though. All right. So let g be the function given by g of x equals integral from -4 to x of f of t dt. So here is the graph of f. Okay, so graph of f is given to us. The integral for g is from -4, so that's good, right? We're starting kind of at the left endpoint and just integrating to the right here, okay? For each of g of 1, g prime of -1, and g prime of -1, find the value or state that it does not exist, okay? So let's kind of do that here. So, if we want to evaluate g of -1, okay, that is going to equal the integral, right, from -4 to -1 of f of t dt. Okay, we're going to integrate from -4 to -1, right? All we're doing is just replacing the x here with -1, so the x in the integrant, in the limit of, or the upper limit of integration there becomes -1. Okay? How should we go about integrating from -4 to -1 here? What are we going to use? Trapezoid area formula. Exactly right. Okay, so that's 1/2 times the base, which is, again, this distance right here. Or sorry, not the base, the height. The height of the trapezoid is this distance right here. So it's going to be 1, 2, 3. Oh, I'm sorry, there, like that. Okay, height. And then base 1, we'll say it's this base right here, which is a height of 3. And base 2, which is this height right here, we'll say it's a height of 2. Okay. Now, this is going to give us the area, but what do we need to add to this in order to kind of give the correct value? We need to make it a negative. Okay, why do we need to make it negative? The curve is below the x-axis, so we have to say negative. And we're integrating from left to right, so it's going to be in a kind of like a positive direction, but it's under the x-axis, so it's going to be a negative value. Okay? And so you end up with, let's see here, 5 times 3 is 15, so negative 15 over 2 is that. Okay? Let's try g prime of negative 1. Okay? Now, if I want to take the derivative of this, what will the derivative of this function be? F of x. Yeah, just x. Right? This is second fundamental theorem of calculus. The x replaces the t here, so it'll be f of x times the derivative of x, which is 1, minus then f of negative 4 times 0. Okay? So let me just, well, yeah. So maybe I'll do g of x here. And you don't need to write this out. You can go ahead and just do it if you want to, but I'll write it out just because I know some people appreciate seeing the second fundamental theorem of calculus just applied here. Okay, so there it would be if you use the second fundamental theorem of calculus, and you'll see that g prime of x is really just f of x. Right, and so then g prime of negative 1. Okay, what is g prime of negative 1? Well, that's f of negative 1. And what's f of negative 1? Negative 2. Okay, and then how about g prime prime of negative 1? What will g prime prime of negative 1 be? What will be the derivative, so which is then f prime of negative 1? What is the derivative of f at this point? Does not exist, right? Does not exist because it's pointy there. Don't need to justify it. We can just say it does not exist. And that is sufficient. Okay. Questions on A? All good? All right, let's try letter B. I'm going to try and squeeze letter B in over here. We'll see how well that works. Okay. Letter B, for the function g, defined in part A, find the x-coordinate of each point of inflection of the graph of g on the open interval from negative 4 to 3. Okay? So, how do we normally find points of inflection? What do we look at? Second derivative of the function. If we want to find a point of inflection of the function, we look for the second derivative. Okay, and we want to specifically know where the second derivative is changing from what to what? Positive to negative or vice versa. Right. Okay. Well, do we have the second derivative? What is this? The first derivative. Okay, so can we use the first derivative to find points of inflection? Yes. So if the second derivative is changing from positive to negative, what's happening in the first derivative? Increasing to decreasing, and then if the second derivative is changing from negative to positive, the first derivative will be changing from decreasing to increasing. So, at any point in here, do we change from increasing to decreasing or decreasing to increasing? Yes, at 1, 2. So, where do we have a point of inflection? At x equals 1. Okay? So, and again, it just says find the x coordinates, all we have to do there. So, at x equals 1, there is a point of inflection for what function? G. Because g prime of x, which is equal to f of x, changes from, and in this case we can be specific because there's only one behavior, so we can be specific and just say changes from increasing to decreasing. We don't need to add the vice versa there. I mean, we could say it, but it's not necessary. Changes from increasing to decreasing at this point. Okay? Increasing to decreasing at this point. All right. So that's all we need to say there. All right, letter C. Letter C. Let h be the function given by h of x equals the integral from x to 3 of f of t dt. Find all values of x in the closed interval, negative 4 to 3, or negative 4 less than x, less than equal to x, less than equal to 3, for which h of x is 0. Okay, for which h of x is 0. Okay, so we want to integrate our function here, f, from an x value to 3. So instead of talking about from a number to x, we're now saying the lower limit is our variable here, where we start integrating, and then up to the 3. Okay? So right here we can see there's our 3, and we kind of want to think about integrating kind of like backwards almost to kind of cancel out this area here. Okay? So let's see. All right. How can I do this with some sort of method here? Well, I guess I'll open up to you guys. Any ideas about maybe like an x value that would result when we integrate from that to 3? It will kind of like be h of x will be 0 there. Any ideas? Yeah, Landon?
3.
Okay, so 3. Okay, so yeah, so x equals 3 would be a good answer there, right? The integral from 3 to 3, okay, is included in that interval, and that would give h a value of 0 there. So yeah, so x equals 3. Okay, the integral from 3 to 3 of f of t dt, okay, which would be 0. So very good there. That would be one solution. Okay. Is that the only solution? I didn't even think about that one, Landers. A good job there. Yeah, Lily. What's that? 1? X equals 1. All right, so let's check it 1 here. All right, so h of 1 is going to be the integral from 1 to 3 of f of t dt. Okay, if we integrate from 1 to 3, we are going to accumulate some area here, but what's going to happen with those areas? Right, they're going to cancel, right? We have this positive triangle here, but then by symmetry, we have the exact same negative triangle right there, and so those will cancel out and result, yes, in that integral being 0 as well. Okay, are there any more? Matthias? -1, very good. Okay, because now from -1, we will accumulate this negative triangle. That will cancel out by this positive triangle. And then this positive triangle will be canceled by that negative triangle. And so, yes, x equals -1 is also a solution there as well. Okay? And that's it. We can kind of convince ourselves we're done at this point, because if we pick any point earlier than that, we're going to have just a bunch of negative area that will not be canceled out by the positive area there. Okay? So things to look for situations like this, right? You're kind of looking for what makes the integral 0, so you want positive areas to cancel out with negative areas and vice versa, and negative areas to cancel out with positive areas. If we go any further back here, we're just going to accumulate more kind of negative, or if we start from any further back, we're just going to accumulate more negative area, which then will not be able to cancel out. Exactly. Okay. So yes, that was exactly right. Very good. Okay. That one I don't really have a good way to explain that one other than what we just did there. Okay. So any questions on letter C? Does that make sense? Somewhat there? All right. So let's try letter D then. All right, for letter D then, for the function h defined in part C, so we're still using h now, find all intervals on which h is decreasing. Explain your reasoning. Okay? How do we determine when a function is decreasing? What do we look at? Its derivative, right? And we want to know specifically when its derivative is what? Negative, right? Okay, so we're going to find the derivative of h of x here. So if h of x is the integral from x to 3 of f of t dt, okay, then h prime of x will be what? It won't be f of x. It will be negative f of x. Exactly right. Let me show you the steps here, okay? And it has to do with where our variable is. It's the lower limit of integration. Remember, we always subtract the lower limit of integration. If I just do the second fundamental theorem of calculus, you'll see it show up, right? So if I take the derivative of this integral, the 3 gets plugged in. It's f of 3 times 0, though, because the derivative of 3 is 0, minus f of x times the derivative of x, which is 1. And so h prime of x is negative f of x. So we have to be careful with that, okay? Because the limit of integration, the x is in the lower limit there, so it's going to end up being negative f of x because you subtract that lower limit there. Okay. So that negative f of x, all right, that's what we're going to use here. And so we can use our graph. But how does that affect our graph? This is the graph of f, And we're thinking about negative f of x. So how does that affect what our graph looks like? It reflects it over the x-axis, exactly right. So ordinarily, if we want to know where h is decreasing, we normally would look for where h prime is negative. But because this is reflected over the x-axis now we want to look at our graph and see where h prime is what? Positive, okay, because it's the opposite, okay? So what's the interval here where h would be decreasing? 0 to 2. 0 to 2. So you can say something like, h is decreasing for 0 less than x less than 2 because f is greater than 0 on, let's see, how do I want to do this? That interval. So h prime of x, which is equal to negative f of x, will be less than 0 on that interval. Okay, something like that. Okay. Don't forget to give those explanations, right, for your justification, or explanations when it asks you to. Okay? So there's our answer. Okay. Questions on any of that? All right, cool. So let's read through this next one here, and then maybe I'll give you guys a chance to try it on your own. All right. So this one looks a little bit funkier. So you're like, great, thanks for giving us this weirder one here. So the amount of water in a storage tank in gallons is modeled by a continuous function on the time interval 0 less than or equal to t less than or equal to 7. So that's our interval, where t is measured in hours. In this model, rates are given as follows. Okay, so I there, the rate at which water enters the tank is f of t equal to 100 t squared sine of the square root of t, gallons per hour, for 0 less than or equal to t less than or equal to 7. And the rate at which water leaves the tank is, and we've got this, it's a piecewise function. G of t is 250 for hours between 0 and 3, including 0, and 2,000 gallons per hour for the interval between 3 and 7, including the 7. Okay, the graphs of f and g, which intersect at t equals 1.617 and t equals 5.076, are shown in the figure above. Okay, so that's good to know those. You can even label those, maybe not be a bad idea. So t equals 1.1617 and t equals 5.056, 0.76. Okay. At time t equals 0, the amount of water in the tank is 5,000 gallons. Is this important information? Yeah, right. We need to know how much water is in the tank. Okay. So letter A, how many gallons of water enter the tank during the time interval from 0 less than or equal to t less than or equal to 7? Round your answer to the nearest gallon. Of course, this would be a calculator active question. Okay? So go ahead, take a couple minutes here. Just answer letter A if you'd like. Just answer letter A if you'd like. Okay, set it up. And just answer letter A there if you'd like. Okay. And find how many gallons enter the tank. Make sure you round your answer to the nearest gallon. Okay. Please don't forget to set up your integral. Show your integral setup too, right? That's part of your work. Don't just give an answer, show your integral setup, because oftentimes you get points for showing that integral setup too. So please make sure you're showing your integral setup. So we only want to know about counts entries. So yes, good. That's very good. And it's, if you don't have to write this out, you could just say yeah. Yes.
How do you do the integral?
Sean, right there. What's that? Math 9.
Oh no, I mean the.
Second, and then math 1, which is the test. And then there are your symbols and stuff.
So I think mine's a little bit different.
Yes. What are you trying to do?
I'm trying to integrate.
Okay, so you math 9. Should do that. Okay. Yep. And so you gotta type in. So for that command, since you don't have the pretty type, it goes your function with respect to x, and then a, and then b. Like that. Okay, that's how you always think about it. John, just have a question. You're good now. All right.
That's good.
Oh, it's an upper, lower level. With x over x, you get 1 no matter what.
So your setup looks good, but oh. Okay. Try and see that. All right. So I think we've got enough time here for that letter A, right? So should have gotten 8,264 gallons. Okay. We do not add the 5,000 to this one. But Mr. Wade, last time for Camp Newton, we added the initial amount. But what is the question asking here? How many gallons of water has entered the tank? Not how many gallons are in, or how many gallons are in the tank from 0 to 7, right? Just how many gallons of water have entered the tank. Okay, so it's just the integral there. Okay, the net change. All right, questions on A? Are we ready to move on to B? Yes. Okay, so letter B. For 0 less than or equal to t less than or equal to 7, find the time intervals during which the amount of water in the tank is decreasing. Give a reason for each answer. Okay, so we want to know when the amount of water in the tank is decreasing. All right, what is affecting the rate of the change of the water in the tank here? What functions are affecting the rate of change of the amount of water in the tank? F of t, okay, for the water going in, and G of t, both of those things, right? And so we want to know find the intervals during which the amount of water in the tank is decreasing. So it means we want to know when that is going to be negative, right? So f of t, let me do it this way. We'll say a prime of t for the amount of water in the tank, the rate of change of the amount of water in the tank. Okay, is equal to the amount going in, f of t, minus g of t. Okay? And we want to know when that is decreasing. So we want to know when this quantity is what? Negative or less than 0. Okay? So we're going to say when is f of t minus g of t less than 0? Okay. Or when is f of t less than g of t? Okay. Do we need? Yep, Gabe.
So I knew it should have been f of t minus g of t, but what tells you that?
Okay, so do you understand that? So I guess let me back up one step here because I maybe did too much of a jump for this case. So we want to find the time intervals during which the amount of water in the tank is decreasing. So we want to, or you understand we want to look at the rate of change of the amount of water. So you're good with that. So there's two things affecting how the amount of water is changing in our situation here, right? We have water getting poured in, water getting pumped out.
Yeah, I just wanted to know, like, why not, like, GFT minus FFT?
Okay, so which one is describing the rate at which water is entering the tank? F of t. And then we want to take away G of t, because that's removing that water at that point. Okay, so G of t, if you were to just like come up with that like value, or if you were to integrate G of t, it's going to give you a positive number. It's saying this positive amount of water is being pumped out. So to show the removing of that positive amount, you have to subtract the rate. Okay, subtract it kind of thing. Okay, now, how are we going to determine when f of t minus g of t is less than 0? Or how can we see when f of t is less than g of t? What can we look at? We've got a graph right there, don't we? We've got a graph. Isn't this f of t right here? And this is g of t. And g of t here as well, right? So we know the intervals here without having to go to the graph. I mean, we could graph it on our graphing calculators if we wanted to, right? But they provide the graph for us. Why not just use this, right? Why not just use this? Okay? Why not just see? Now, of course, you could, if you wanted to, kind of like, you could do this. So you could use your graphing calculators and do, f of t minus g of t. I would suggest that you do it 2 different times. You could look at, f of t, your function here, and then for the interval from 0 to 3, you could subtract 250. So do f of t minus 250 and look between 0 and 3, see how many times it's below the x-axis there, or how the interval for the below the x-axis there, and then you do a separate interval for x values between 3 and 7 when you do f of t minus 2000, and again, see where it's below 0 there. But again, we could just look at the graph here. So where does f of t start being less than g of t? At 0 to 1.617, and then again from 3 to 5.076. Yeah, okay, the 3 there, right? It starts being below again. Yep. And so that's our answer. Okay. So from 0, we could say, let's see here. Yes, scoot it up so you can see that. Yeah. So let's see. I want to make sure I answer the question in the way it's asking. Okay. So I'll say for 0 less than t less than 1.617 and 3 less than t less than 5.076. Okay, Clayton, question?
Would it matter if we use brackets around the values that are given in like parentheses around 3 because it's not included? Or is it different because we're talking about rates?
I see what you're saying there. I think you could include the 0, I think, but you would want to exclude the 1.617 and I would say exclude the 3, and then exclude the 5.076, I think. So I think you could include the 0, but I would exclude the other endpoints, though, I think. Okay, so because it says give a reason for each answer, okay, so because f of t is less than g of t, right, that's what we're looking for on those intervals. Okay, or you could say, or bless you, f of t minus g of t is less than 0, that quantity. So you can say it either way there, one of those 2. Okay, that'd be part B there. Okay, so that was part B. And then part C, all right. For 0 less than or equal to t less than or equal to 7, at what time t is the amount of water in the tank greatest? Or, in other words, to the nearest gallon, compute the amount of water at this time. Justify your answer. So not only find the time at which the quantity of the water in the tank is the greatest, but then also find that quantity of water as well. So in other words, this is asking for what? Absolute maximum. Okay, so we want to find the absolute maximum, which means we need to consider our critical values and our endpoints of our interval. Okay, so let's see here. What are our critical points? Yeah, the zeros. Where does this or what are the zeros here for our derivative? Well, it's when f of t is the same as g of t, right? Where is f of t the same as g of t? 1.617 and then 5.076. Okay, so you've got our critical points. We have the endpoints of our interval, so now it's just a matter of coming up with which one gives us the greatest value. Okay, which one gives us that greatest value? Okay, so let's see here. So let's write an actual function now, and maybe I'll use x here instead of t. I'll use x. Okay, so let's use an actual x here. So how much water starts in the tank? 5,000. 500. 5,000. And they're going to add to that the integral from 0 to x, we'll say, okay, depending. And then we're going to add in f of t, but subtract g of t, dt. Okay. So there's our setup to describe the amount of water in the tank at any time x. Okay. Starts at 5,000. We're going to add the net change from 0 to x of the water in minus the rate of change of the water in minus the rate of change of the water out, the integral of those things. Okay, the accumulation of that. And so now we're just going to take turns plugging these things in. So a of 0, what will a of 0 be? It's an easy one, right? 5,000 is where we're starting. Okay. Then we'll do a of 1.617. Okay. Which will be 5,000 plus the integral from 0 to 1.617 of f of t minus g of t. What will g of t be in this case? 250, right? Because our t value, 1.617, is between 0 and 3. So it's going to be minus 250 dt. Okay, so that's all we have to do for that one. Okay, so I'll do that here. I think I have that in, don't I? 100. Yeah, okay. So we do 5,000 plus math 9, integral from 0 to 1.617 of nope, not y3. y1. Okay. Stephen showed a shortcut, by the way. I don't know if you guys, if you guys are interested in this. Is another way to do it though, and it does save one keystroke. I think he said I think so. If you want to get to the y1 without having to go through vars and y bars, again, depending on the kind of calculator you have, some calculators, if you press the alpha button and then trace, it brings up this menu here where you can see your different y variables show up, and so we'll just select y1 there and go from that. But I don't know what calculators have that capability, but mine did at least. Oops, I forgot. Darn it. The minus 250 there. Okay, there we go. Okay, so I get 4,719.223. Okay. And then for A of 5.076, now we're going to have to be a little more careful. Okay. How are we going to take care of this? Because we have to integrate from 0 to 5.076, which if we go back up to our function here, 5.076 is in this interval, which means we're going to be into that subtracting 2,000. But at the same time, we're going to be subtracting 250 as well. How can we account for these two different values of g depending on where we are in our interval? What can we do? What can we do with our integral? Yeah, Matthias?
Okay, so solve the way from 0 to 1.617.
Okay.
Okay, so you have to use like the range or whatever for the integral.
Okay.
So you use 0 to 3 for the first, and then you use 3 to 5 for the second.
Exactly right. We have to break up our integral. Right, exactly right. So this is going to become 5,000 plus the integral from 0 to 3. Okay, we're using 0 to 3 because Matthias quickly identified there, that's going to be the complete interval for the 250, which will then be f of t minus 250 dt. And then we're going to add to that the integral from 3, as Matthias said, to 5.076 of f of t, not minus 250, but now minus what? 2,000, because that's the interval we're on there. Yeah, I'm kind of running out of space, but there it is. Okay, so we have to break up that interval. Okay. That's 9, 0 to 3. y1 minus 250 dx plus math 9, 3 to 5.076. Minus 2,000. All right, let's see if I get this all right here. Yep. Okay. dx. And I get 4,016.881. Okay. All right, and then the last one we get to do is, of course, the right endpoint A of 7. I'm just going to squeeze that in over here. And then now that Matthias has kind of showed us how to do the 5.076, you can imagine what we're supposed to do now for the A of 7. Same thing, except we're going to go from 3 to 7 now here. So 5,000 plus the integral from 0 to 3 of f of t. And I guess what I could do, well, all right, whatever. You could just do, I guess, this amount plus the integral. But anyway, we'll just do it. Minus 250 dt plus the interval from 3 to 5 or to 7 of f of t minus 2,000 dt. Okay, so there's that last one there. So the good news is I can just hit second enter and change my upper limit of integration here. Okay, and again, for those of you that don't know, right, so like what I did here, ooh, let me clear this whole thing out. Okay, so what I did here is I hit second enter, and it brought up the previous thing that I had typed. Okay, if you didn't know that, that's something you can do. Like the previous thing that you typed in your calculator, you can hit second enter, it'll get it. Also, again, for some of you, you can like scroll back up to previous things you typed in, hit enter, it'll recopy it down there for you too, so you don't have to like retype the whole darn thing, just what you need. And we get 4,513.807. Okay, these are all in gallons, of course. So, at what time t is the quantity of water in the tank the greatest? 0. Man, that is frustrating, but there it is. Yes.
We should have to do t equals 3 too.
Do we need to do t equals 3?
Yeah.
Oh, I see what you're saying. Let me think here. Yes, because the derivative wouldn't exist at 3. So you're right. We need to include 3. Yep. So it may not be a of 0. It might be a of 3. And I'm guessing it's going to be a of 3, right? So we have to include a of 3 here, right? Because the derivative, the rate of change here, a prime, right, does not exist at 3, right? It's undefined there. And so I'm sure we're going to end up with the answer here because, this is a mess. Okay. Well, thankfully, it's just that quantity there. So 5,000 plus math 9, integral from 0 to 3 of y1 minus 250. And there it is, yes. 5,126.591 gallons. Okay, so that would be our answer there. Okay, so right, so be careful, all right. Yes, we want to know when the derivative is 0, but we also know when the derivative does not exist. And the derivative would not exist, the derivative here would not exist when g of t is 3, or when t is 3, because g doesn't exist at 3 there. Okay, so something to keep in mind there as well. All right. That was fun. Okay, so there's that. Okay. So these are not easy, right? These are not easy. But the good news is, okay, so let me just kind of give you some hope here, right? Okay. If you can get 6 out of the 9 points that are available, so every response question, 9 points. If you are getting on the regular, what would equate to about 6 out of the 9 points, which is like 66%, 2/3 of this right, you're on track for getting a 5, right? I mean, just keep that in mind, right? If you can get 6 out of the 9 points for these free response questions, you're on track for getting a 5. So that should hopefully be encouraging, right? It's not necessarily expected you're going to get all 9 points here, and that's going to require you to, for you to get the 5. Of course, you want to get as many points as you can, but if you can stay on track for 6 out of the 9 points for each one of these questions, that's 2/3 of the points, and that's going to get you on track for a 5. Okay, so keep that in mind. Okay, don't be too discouraged if you're like, I couldn't get this whole thing 100%. That's not the expectation. The expectation for the AP test, 6 out of the 9 points. Okay, so we'll continue on with this tomorrow. For now, I've got your assignment. I'll also pass back your problem sets too here. Now that Cassie's recorded for me. Okay. Your homework is 1 question on this paper I'm passing out. Why is there more than 1 on here? Well, because this one, it's just had another AP question. The back is going to be your homework, I think, for tomorrow night. So the only one you have to do here is this number 3 for homework tonight. Wow, number 5 for this homework tonight. Oh, now I want to check to make sure that I read that correctly. Yes, 2003B, number 5. That's this guy right here, or this girl, or whatever that problem there. Okay. Number 5.
Yeah. Only word on
Is he going to tell us what you can do?
Yes, number 5.
We only do number 5?
Only number 5. If you want to work on tomorrow night's homework, it's the one in the back, number 1. Oh, that's next one. Oh, I'm sorry. I was so focused on that. Why is X not 7? Because, so imagine you put a 7 in there. We're saying this thing is a function. We're saying A of X, but where is our X then if we don't have an X? So, but is it always 7? True, maybe over here I should say then for 0 less we put X less equals 7. Okay? So, this is F. Here's F at -1. What is the slope at -1? Right, what's the derivative of that at -1? Right, but that's a good point, right? So it still matters though, the facts. Yes, it still matters because I'm just gonna get these guys there.
But I also qualify for absolutely 0 financial assistance. That was all merit.
It's a point. It's not a pointy point, but it's still a point, right? A sudden change in slope.
Almost.
Exactly. So the derivative would not exist here either.
I'm not going to.
Okay. So like there, you definitely agree the derivative would not exist. Because it's like super point. But same principle here. What's the slope to the left of -1? It's going what? Up 1 right 3, so 1/3. And then the slope here is like up 2 right 1, so 2. So it suddenly changes from 1/3 to 2. So what's the slope? Well, from the left it's 1/3, from the right is 2. The slope at that point.
What if it was like,
If it was curved, right? Then,
so it can be different, 3 to -2?
but it's a gradual change as opposed to such. You see what I'm saying? We're jumping. Like, x squared. Right? F of x equals x squared looks like this.
Yeah, I would get that.
To the left is positive, or sorry, to the left is negative, to the right is positive, right? Its derivative, right, this, okay, if I graph that here, it's going to look something like this. right? Okay, so there's no problems with that derivative, right? The derivative, the graph of the derivative, the line, there's no problems with it, right? It's just like a nice smooth function. Oh, I'll take. Well, actually, I'm going to pass them out because I want to talk to some people when I pass them out. So I just make so this is kind of describing. Now let's compare it to this. Okay, absolute value of x like that. Its derivative is this. Oh, question? Yes. Oh, no, I gotta think here. Okay. And so it's gonna look like this. You see the difference? This is a sudden change in slope from -1 constant to +1 constant, so it has to jump up like that. The derivative will be undefined, or not doesn't exist at 0. Here, it's a smooth slope, smooth curve, right? Smooth line. Do you see the difference there?
Yeah.
It's a smooth transition. Yep. Yeah, the problem is here we don't hit every slope value between -1 and 1. We jump from -1 to 1 suddenly. In the x squared example, we hit every slope between those points. That's it. All right, we can stop this video now. E.